the next theorem that I'd like to introduce, you might even call it a lemma, because really it's just used to help prove the fundamental theorem of finite cyclic groups, is that subgroups of cyclic groups are cyclic. That's the sort of shorthand for the theorem. What the theorem says officially is that every subgroup of a cyclic group is of the form the group generated by g to the m for some non-negative integer m. You can pick this integer to be non-negative as part of the statement of the theorem, and in particular, every subgroup of a cyclic group is cyclic. I'm going to put the text for the proof up into the slides. In a perfect world, I'd go through this proof in great detail. However, in the interest of time, and because this is a very famous theorem and you can find these things elsewhere, I'm just going to gloss over the main ideas of this proof. It's somewhat a follow-your-nose proof with a standard trick or two from abstract algebra. So the idea is, take a cyclic group, write it the way that we write cyclic groups in terms of a generator, and then the format of the proof will be to start with an arbitrary subgroup and to show that it is the group generated by g to the m for some non-negative integer m. The identity subgroup is really easy to deal with, so you can assume that you have this subgroup that contains a non-identity element. Using the fact that you've got a cyclic group here, you take this non-identity element and write it as a power of the generator of the group, which is what you always want to do in these groups. At every opportunity, use the fact that the group is cyclic to talk about everything as just a power of that generator. And it turns out that what you're going to want is, we started with an arbitrary element of h that was written as some sort of power of the generator. That's not necessarily going to be the generator for the subgroup h that you've chosen. You've done a lot of choosing randomly. You really need to choose properly in order to find the generator for the group h. So it turns out that if you take m to be a number strictly larger than 0, and you take it to be the least integer with the property that g to the mth power belongs to h, then what turns out to happen is that that element, g to the m, is the generator for this group h, and that must be proven. So that's the theory of the proof and the idea behind it, but all of the details are on here. You use a little division algorithm here, and you use the property that you've really and truly got the least power here in order to conclude that this k you started out with is actually a multiple of the number m, which is what you want to do. So like I said, I'm not going through this in great detail. I've hopefully talked long enough that if you wanted to just read the answer right off the slide, you could pause it right now and go through it. Otherwise, as I said, the proof is done pretty well in Gaussian. What I'd really like to do in this video is walk through using the two theorems that we covered previous. I'd like to use those two theorems to prove the fundamental theorem of finite cyclic groups. You really have to prove anything when you precede it with the fundamental theorem of. That means it's one of the most important theorems that you're going to encounter as you're going along, and that is in fact true of the fundamental theorem of finite cyclic groups. What this theorem says in a nutshell is that cyclic groups, you can say basically everything you want to say about them. You get really lucky, and they have all of these properties that we've noticed so far working through cyclic groups are true of all cyclic groups, no matter what, and they're somewhat easy to describe the structure of. So here's the theorem. Let's suppose that G is the group generated by little g. We're assuming that G is a cyclic group of order n. We're writing little g for the generator, and the size of the group G is n. The first part of the statement of the fundamental theorem of finite cyclic groups is that every subgroup of the group G has order dividing n. But you can say something, in fact you can say more, that if you started with a divisor d of the integer n, then there is a unique subgroup of that order, and you can put a finger on precisely what subgroup it is. It's the group generated by g raised to the n over d power. So again, we do have to have this toggling. Think about this theorem that we covered before about the order of an element is really n divided by the greatest common divisor of sort of that power of the element. So you do have this little division flip-flopping business that's going on, but there is a unique subgroup, a unique cyclic subgroup in fact, of order D. So here's the proof. Again, I'm going to take the previous two theorems that we've covered. We're going to need both of those theorems. I'm going to take those as a fact, and then we'll walk through the proof of this theorem under those assumptions. So let's begin by taking H to be an arbitrary subgroup of the group G. By the previous theorem, we've seen that every subgroup of a cyclic group can be written as the group generated by G to the m, where m is some sort of positive integer. Now, we've also seen by the other theorem that we covered in the last set of videos that if we're looking at the group generated by G raised to any old integer power, in this case G to the m power, that's the same as the group generated by G to the greatest common divisor of the order of the element and the integer power that you're looking at. So the group generated by G to the m is equal to the group generated by G raised to the GCD of n and m power. And furthermore, the order of the element G raised to the GCD of n and m is n divided by that value. Well, truly it would be divided by the GCD of n and n comma m, but n comma m, the GCD of n and m does divide n, so that's what gets put in right here. We conclude from that if H is equal to the group generated by G, and that's exactly the same group as the group generated by this, then the order of H is equal to the order of this element, which is n divided by the GCD of n over m. Now, n divided by, recall, the GCD of n and m, it's the greatest common divisor of n and m. In particular, the GCD of n and m divides n. So when I'm looking at this quantity, n over the GCD of n and m, that's an integer, and in fact it's a divisor of n. So we've completed the proof of this first sort of statement here. We've taken an arbitrary subgroup H by writing it as a group of the form the group generated by G to the m for some m. We were able to conclude that the order of H divides n, and that's the first part of the statement of the theorem. In fact, we've done a little bit more here. We've used that theorem that we discussed in the last set of slides to show that an arbitrary subgroup of the group G can actually be written not just as the group generated by G to the m, but as the group generated by G to the D, where D is a divisor of n. In particular, it's the GCD of whatever element it was here and the order of the group. Now let's go on and let's take a look at the second part of the statement. We want to show, in fact, that no matter what the divisor D is of n, there is a unique cyclic subgroup of that order inside of G. So only one subgroup of each order, and for every divisor there is one. Just a really strong property, not true of all groups in general, but true for cyclic groups. So let's do this. Let's start with an arbitrary divisor of n, and let's show that G has a cyclic subgroup of that order first. And then we'll work on showing the existence first, and then the uniqueness second. So let's take an arbitrary divisor. Let's let D be that divisor. And by the theorem that we covered in the last set of slides, if I can express D as n divided by the GCD of n in some integer, then I will be able to find an element that has order D. So doing a little bit of arithmetic here, we find that the element, so D is a divisor of n, so n over D has a meaning. If we take G raised to the n over D power, according to this theorem, the order of the element G raised to the n over D is n divided by the GCD of n and n over D. The greatest common, remember that n over D does in fact divide n, so the GCD of n and n over D is n over D. And when you simplify this sort of complex fraction, in the end what you get is D. Now this establishes that G has a subgroup of order D. In particular, it's the group generated by G raised to the n over D power. And this was true of an arbitrary divisor d of n. So G, in fact, does have a subgroup of order d for each divisor of n. All the way back to our first example, we noticed in both Z mod 12Z and in U of 13, both cyclic groups of order 12, we noticed that we had a subgroup. We had subgroups of order 1, 2, 3, 4, 6, and 12, and each of those groups happened to be cyclic. So this is something that we saw before, and this is in fact true of all finite cyclic groups. Now we've done existence, let's now do uniqueness. So we've shown that G does have a subgroup of order D for each divisor of n. Let's start then with an arbitrary subgroup of order D and show that it's in fact equal to this subgroup, this cyclic subgroup that we found in the first paragraph. So let's start with H, an arbitrary subgroup of order D. We have seen in our previous theorem, we don't know a priori that H is the group generated by G to the n over D, but we do know that we can write H as the group generated by G to the m. And we saw that a little bit more was true. You know, from the theorem we saw that m was just some sort of positive integer, or I guess I should say non-negative integer. However, on the previous slide we saw that we may assume that m is a divisor of n. So that's going to help us a little bit to make things a little easier. So m is a divisor of n, and because H is a subgroup of order D, and H is the group generated by G to the m, we know that the order of H, which is D, is the order of this generator, G to the m. So the order of G to the m is equal to D. By the previous theorem, which tells us how to compute the orders of powers of G, we have that the order of the element, G to the m, is given by n divided by the GCD of n and m. But because m is actually a divisor of n, the GCD of n and m is m. So this quantity right here, n over the GCD of n and m, actually simplifies to n over m, and this must be equal to D. If we rearrange this equation and solve for m, we find that if we assume that m is not just a positive integer, but if m is a divisor, which we've shown that we can do, that m is in fact n over D. So H was just some group generated by G to the m, but if we make the assumption that m is a divisor, then m is equal to n over D, and this shows that H is in fact not just the group generated by G to the m, but it's equal to this previous subgroup we found that has order D, and therefore there's only one of these subgroups that has this order.